In this video, I'm going to be working AP Pre-Cal Homework 9.1, which is all about inverse trig. So the first one's asking us to fill in tables of values for inverse sine and inverse cosine. So I am going to start by reminding you that, okay, I probably should start with a half circle first, or maybe the whole circle. And reminding you where we're looking when we think about arc sine. Okay, that's really, really important for us. Okay, when we have inverse sine, we are looking on this part of the circle here. Okay, right there. Okay, that will run the full range of sine. So we're looking for the most obvious place on the unit circle in this, in this region here, where sine x equals, for instance, -1. Okay, where does sine equal -1? All right, the first one, no, that's not one. The first one here, okay, that's where sine is equaling -1, down at the very bottom of the triangle, or the very bottom of the circle. And that's going to be pi over, or negative pi over 2. And remember, this is negative pi over 2 to positive pi over 2. Okay. Then -1/2. When is sine -1/2? That would be right down here, which would be right over there on the circle. And that would be negative pi over 6. Where is sine equal to 0? Okay, well, there's no vertical displacement from the y-axis. That's what sine is. Okay, that would be right there at theta equals 0. Remember, inverse sine is giving us the theta on the unit circle that corresponds to a given sine output. All right, so it's going to be theta equals 0 there. So inverse sine of 0 is 0. Okay, inverse sine of a half. Where on the circle, pardon me, where on the circle is sine most obviously equal to 1/2? And that would be right here at pi over 6. Okay, not very far up on the y-axis. That's what a half is. It's the first stop on the unit circle is what I like to say. Okay, so that's theta equals pi over 6. And where is sine equal to 1 on the unit circle? Where is it most obviously equal to 1? Right here at pi over 2. Realizing that, I always say most obviously in calculus because it's like, it's been a long time, and it's like, hey, where's the most obvious place where tangent equals 1? That's a really common one in Cal BC. I think for y'all, we did a really good job of training you on saying like the fourth quadrant angles, thinking about 5 pi over 3, 11 pi over 6, 7 pi over 4. But for now, we're going to need to be thinking about those fourth quadrant angles as negative values. And to me, that's more obvious, but I know that to y'all, like the way that we learned it, it was, thinking of it as just short of 2 pi. That was really good. I really liked that. But here, it might be better for us to think about these fourth quadrant angles as negative, and we're going to need to do that. Okay, so for inverse cosine, I'm going to draw another circle and draw some axes. Okay, that ended up being, okay, that's pretty good. Okay, for cosine, let me get a highlighter. We are looking in this part of the unit circle, right? Because that will be the full range of cosine from -1 to 1, right? Because cosine is the horizontal displacement from the y-axis. Okay, so the first one here, okay, -1. Where is cosine most obviously equaling -1 on the unit circle? Well, there's only really one place, and it's the far left edge, and we think of that as theta equals pi. So output is pi. When is cosine -1/2? Okay, well, when I go over here, I really like those halves in this class, it seems like. And that's going to be up at towards the top of the unit circle, but not the top of the unit circle because that's where cosine is 0, no displacement from the y-axis. So if I've got a little bit, that's the first stop beyond pi over 2, which is going to be 2 pi over 3. Then where is cosine equaling 0 on the unit circle? Okay, right there, that's at the top, that is pi divided by 2. Okay, where is cosine equaling 1/2? That would be over here, so it would be like, the last one before pi over 2, that's pi over 3, this is a 60-degree reference angle. So pi over 3, and where is cosine equal to 1? At the far right edge of the circle, that's where theta equals 0. Okay, now we're going to sketch the graph and state the domain of range, and that'll be fine, right? F of x equals inverse cosine of x. Okay, to be honest with you, I have to draw the circle. So that was where we said we were looking at the right side of the circle. It was a really thick highlighter, but you get the picture. Okay, so that's negative pi over 2 to pi over 2. That's the domain of the arc trig function. Wait a minute, no, that is the range of the arc trig function because that's the domain of the original that we restricted, pardon me. Okay, so that is the range of arc cosine is negative pi over 2 to pi over 2. So let's say, all right. Okay, now the domain of inverse cosine is like, well, like what can cosine equal, right? Because that's what inverse cosine is like, I know what the cosine is, I know the ratio, I don't know the angle. Okay, so all of the values that cosine could be, it's between -1 and 1, right? Because on the unit circle, the farthest I can go away from the y-axis to the left is -1, because it's a unit circle, and the farthest I can go to the right is going to be +1. Okay, so the domain will be -1 to 1. Okay, and pi over 2, that's between 1 and 2. And so I think, we're just reminding you, pi is 3.14, so half of that would be 1.57. So I'm looking for like basically 1.5, maybe a little above 1.5, a little bit below 1.5 here. And I'm just going to mark those as pi over 2 and negative pi over 2. And honestly, we just did the work up here, so I think I'm going to go and, just borrow from what I did earlier. When x equals -1, y equals negative pi over 2. So I'm going to be, probably what I'm looking for, about there. Okay, and then when x equals 0, y equals 0. And when x equals 1, y equals pi over 2. But this is not a linear function, right? Because when x is -1/2, I've got pi divided by 6, which is kind of like a half. So I'm going to say, all right, what was it? -1/2, negative pi over 6, which is kind of like a half. And that doesn't really do a very good job. Hold on just a second. Oh, goodness. Okay, I just realized that I was copying off of the arc sine table. Why would I do this to myself? Put the inverse cosine right underneath the table for inverse sine. Very sloppy, pardon me. Life will go on, right? It's going to be okay. At least I caught it in time. So I've got, okay, when x equals -1, y equals pi. Okay, I'm going to change this grid a little bit so I can graph that point, because I don't have -1 pi on this grid right now. Okay, I determined that grid was pretty much hopeless, so I'm just going to make my own here and, keep working. So I'm going to need to mark off -1 and +1, which should be about the same distance. That looks pretty good to me. And then I need y to go from 0 to pi, so I'm just going to decide whatever I think that is. Maybe I'll put that all the way up here. And then I've got pi, half of pi, a third of pi, and 2/3 of pi. So I think the scale might be a little off here, but the shape of the graph should be good. Pi over 2, and then pi over 3 and 2 pi over 3, relatively close to pi over 2. Okay, and now I can make myself a good sketch of the graph. -1 pi, I'd say it's about there. -1/2 and 2 pi over 3. 0 and pi over 2. Oh, it's going to look linear again. 1/2 and pi over 3. I just really don't like graphing arc trig. And then there. Okay, on the right side you can see the concavity a little bit better than the left. But it's supposed to be concave up through here, and then concave down through there. And okay, so what I'm going to do, I'm going to adjust my point to fit the curve, right? And that's going to be 2 pi over 3, and I'll just say that's a half right there. Okay, so that's going to be the best graph of arc cosine that I've got. And I'm, pledging you that we do not need you to produce a whole lot of graphs of arc trig, beyond this problem right here on the homework. What we need you to be able to do is pick these out of a photo lineup, right? In a multiple choice setting, we need you to be able to reason with the graphs. But I think that's not going to be, based on the curvature of the graph, but more based on key points. Okay, so inverse sine of x. All right, so yeah, I'm just gonna copy from the table. X runs from -1 to 1, right? Y runs from -pi/2 to pi/2. This is the graph I was originally trying to draw earlier. It just didn't make any sense. All right, so go over here, -pi/2 there, +pi/2 there. Let's see. -pi/2 comes from -1. So right here. Then 0, 0, and then let's see, what is it? A +1 pi/2. And then the other points are just somewhere in the middle, but again, -1/2, -1/2. I guess that would be indicating that type of curvature. Yeah, I can see it a little bit better on this one. Maybe it's because I had a grid. I am going to go check off on a different screen real quick and just make sure. I just want to be totally sure about this. Yeah, that is the right concavity. As you can maybe tell, I don't have a lot of experience graphing arc trig. This is not something that we're going to be needing to be able to do in AP Calculus or AP Statistics. So that's why we're not, going to be doing it a whole lot. Nor are you going to be doing it in like later math classes. It's good that you know what the graph looks like. It's good to generate new graphs here and there, but we're not going to be like, super transforming these things and producing the graphs ourselves. Maybe looking at these in a multiple choice setting. All right, inverse tangent of x. Now this is a more interesting graph. Okay, I did not fill out a table for this one, so, and I didn't mention the domain and range. All right, domain for this arc trig function is going to be -1 to 1 because these are the values that sine could be giving us, right? And inverse sine is where saying sine x equals some number. So domain is going to be -1 up to 1. And then the range of this thing, as you can see from the graph, I just let the table guide me, it's -pi/2 to pi/2. But if we think about that part on the circle right here, that right side of the circle, that's -pi/2 to pi/2, and that's the range of the arc trig function. So -pi divided by 2 up to pi divided by 2. Now, tangent, it works a little bit different, right? We have vertical asymptotes on tangent, and we have, if you think about the graph back from, I don't know, a while ago now, had these vertical asymptotes that went up to positive infinity, it also went down to negative infinity. Okay, so we've got pretty much, tangent's going to be able to, run the full range. But in order for inverse tangent to be a well-defined function, just because I haven't mentioned that on this video, for inverse tangent, we're going to be looking the same place we look for inverse sine, which is right there, -pi/2 to pi/2. And then I'm going to just like kind of label a few key points. Okay, this is a place where tangent is 0, right? Because it's sine over cosine. Where's the most obvious place where tangent is equal to 0? That's theta equals 0. Okay, so I'm going to say, so I'm going to compute a few key values. Inverse tangent of 0. In order to find that, I'm going to think where on the unit circle is tangent theta equal to 0. And that gives me theta equals 0. Okay, so inverse tangent of 0 equals 0. Right? Maybe I can get a little bit more room. I'm going to make a table, but this time I'm going to make it horizontal. All right, so x and arc tangent of x. Okay, I plugged in 0, I got 0. Okay, so I'll plot the origin on my graph. Then, I might be interested in graphing inverse tangent of 1. Okay, that one's pretty common. It comes up all the time in AP Calculus. Inverse tangent of 1, where on the unit circle is tangent most obviously equal to 1? Okay, well, tangent is sine over cosine or opposite over adjacent, where the legs equal on a 45, 45, 90 triangle. So that would be up here at pi/4. Okay, and then if I thought about inverse tangent of -1, let's report my finding there. If it was inverse tangent of -1, if that was what I was interested in, then I would say, okay, that's where tangent is -1. Okay. And that would be where the legs had equal length but opposite sides, and that would be down here. This would be the most obvious place, and that would be theta is -pi/4. Okay, now then there's this one other thing that I really want you to know about arctangent, and that's up here. What happens to tangent right there? Okay, what I would say is, as theta approaches pi/2, Okay, we know that cosine is approaching 0 because cosine is the horizontal distance from the y-axis. And if cosine is approaching 0, sine of theta over cosine theta, which that's what tangent is, that's getting closer to dividing by 0. Okay, and meanwhile, think about all my students take calculus. In the first quadrant, as we're approaching pi over 2 from below, okay, put that notation, we don't use that in this class. Tangent theta is approaching positive infinity. Okay, so what I would also add on to this is that the limit of arctangent, as not theta, of arctangent x, as x approaches infinity, that's equal to pi over 2. And surprisingly, that has come up like a couple of times recently in my AP Calculus class, and we've needed it, and people have not had it, and I've had to like talk them back through it. So it's just like really on my mind, I just wanted to point that out to you. And I will definitely say something about that on the graph here. So now that I've got this, I've got 1 point plotted, I've got a couple of other points, including one that's behind my face. Maybe just zoom out some. Okay, we're ready to graph. Okay, when x equals 1, arctangent x equals pi divided by 4, so that's like 3/4. And then when x equals -1, arctangent is negative pi over 4, so it'd be like negative 3/4. And then, well, the limit as x approaches infinity, that's a horizontal asymptote. So I'm going to go ahead and graph pi over 2, which we determined was a little bit bigger than 1.5, but I'm just going to do this because this graph is relatively zoomed in. I'm going to say, all right, well, that means that okay, that's not, it does not look like that. Pretty much what I've got here is there is going to be a point of inflection at x equals 0, and I'm approaching that horizontal asymptote. But there's another horizontal asymptote because as x approaches negative infinity, when does tangent approach negative infinity? Down there at the bottom of the circle, where tangent is negative, all my students take calculus. Okay, only cosine and secant are positive in the fourth quadrant. As I'm approaching negative pi over 2, I'm getting closer to negative infinity in tangent. So I'm going to have another horizontal asymptote through here. And there we go. And this here is exactly why I don't like to graph on a grid. It just like it doesn't ever really look right. And we could go to Desmos, so it would look a lot better. But this was a somewhat valuable exercise for our overall development because we need to at least graph it once, right? I think even y'all recognize that we got a new function type. We have to reason with the graph. We should produce the graph at least once, but maybe once is enough. So state the quadrant location for the inverse trig value. Basically, like where does this number live on the unit circle? All right, so arc cosine of -2/3. So I'm just going to draw the circle and remind you that cosine, arc cosine, I guess is what I meant, takes its values through that part of the unit circle because cosine's horizontal. All right, where is cosine equal to -2/3? Okay, well, right there, horizontally, -2/3 of the way. I don't know, it looks like about -2/3, and that's going to be, some point right here, and that is second quadrant. For arc sine of 1/3, let's start with the circle. Remind you that arc sine takes its values from the right side of the circle. The most obvious places on the unit circle to us, or maybe you're starting to become that way. Arc sine of 1/3, that's where y is a third of the way up to 1. And so I'm going to say, all right, that's right over here, and that's first quadrant, so quadrant 1. Okay, arctangent of positive 1/3, and I mean, I know you can just think about this in terms of like the quadrants that eliminate it down to 2, and then think about where it's positive using all my students take calculus, but I really think we'd be best off reasoning with the circle. Even if my sketches of the circle are pretty rough. All right, arctangent takes its values from through here. Okay, and my options are, first quadrant and fourth quadrant. If I have tangent being positive, that means, x has got to be positive. That means y needs to be positive as well. So basically what I'm saying is that's going to be, I don't know, arctangent could equal 1/3, no, somewhere here. Because opposite over adjacent needs to be the 3 and the opposite needs to be 1. So it'd look about like that. This is looking like quadrant 1 to me. And, okay, it's the next one. Maybe a little too zoomed in. All right, inverse sine of negative 0.8. Okay, arcsine takes its values through here. And I'm just realizing I didn't state the domain and range of inverse tangent, but it's okay. I'll go back and do that right after this one. And so inverse sine of negative 0.8. Negative 0.8 is almost all the way down to negative 1, so I guess I've been marking that in red. So it's like down here, that would go over here on the unit circle. That's going to be quadrant 4. Right, now, going back to arctangent, I'm going to tell you about the domain and range. Well, domain looks like it's all real numbers. That makes sense, because tangent can equal anything, right? We can get the ratio to be really big if we want, okay, by going near pi over 2, having a really tall leg and a really tall vertical leg and a really short horizontal leg. Okay, so opposite over adjacent would be a number really close to 1 divided by a number closer to 0. Okay, we can make that as positive as we want. And then in the fourth quadrant, we can do the same thing and make it as negative as we want. All right, so I'm going to say over here, the domain of arctangent is going to be all real numbers. And then the range, that's stuck between negative pi over 2 and pi over 2. But these are horizontal asymptotes that are not getting crossed, right? Because tangent of pi over 2 does not exist. Okay, so we can't plug in does not exist and to arctangent and get back pi over 2. Okay, that doesn't make any sense. Okay, so we're saying the range is the open interval negative pi over 2 to pi over 2. Okay, and if we were going to write that as an inequality, it would be negative pi over 2 is less than y is less than positive pi over 2. Strictly less than, not less than or equal to. And because we had a few open closed interval issues on the last test when we were solving an inequality. I saw some people were giving me closed intervals when we want open. We gotta be careful about that. Okay, so over here, inverse cosine of 1/5. Okay, our cosine takes its values through quadrants 1 and 2, running the full lateral range. So 1/5 is not very far up. Okay, let's mark that here and say that's here and there. Wait. Yeah, okay, the 2 points, that doesn't make sense. That's the whole idea with the restriction on arc trig, is that this should not happen. Okay, what I did that I should not have done was go on the y-axis, right? We're talking about where cosine is positive 1/5, and cosine is along the horizontal axis. All right, so 1/5 here, there's only one place. So if you're working a problem like this, or you're trying to do arc trig and you're getting 2, okay, that's no good. You have to cut the circle in half, okay, and our cosine is this part of the unit circle, and then go horizontally and find your value. All right, so that's going to be in quadrant 1. I'm kind of glad I made that mistake, though. So I think that's probably an easy one to make. Just careful, sine versus cosine, and also think about tangent. You got to be able to contend with that as well. All right, arctangent of negative 80. Okay, that's one where we're going to have like a really, really kind of skewed triangle. I'm going to even try to draw it for you. Okay, I think in order to do that, I'm going to need this unit circle with like the axes to be pretty close to in the right place. And that looks really good to me. Okay, so arctangent, now we know it takes its values through here. And negative 80, that's going to happen like pretty much. It's got to be like right there. Okay, tangent does all of its increasing and decreasing towards infinity and negative infinity, and kind of like the last moment. But that's how vertical asymptotes work, right? If you think about the graph of regular y equals regular tangent x. Okay, if I do this, then maybe I might switch the pen. If I drew a side here and a side there, nope, that needs to be perpendicular, and I'm realizing that might be a little challenging. Okay, that's going to have to get the job done. And then another side there, and that was my right angle. Okay, I think I have missed the mark. I don't think that the vertical leg is 80 times as large as the horizontal leg, but you get the idea. You see what I'm saying here. I would need it to be really far down, near negative pi over 2. All that to say that we're down there in quadrant 4. All right, that's a good set of questions there. All right, now, number 5. Find the equation of the inverse to the function over the given domain. What are the domain and range of the inverse? Okay, so it's been a long time since we've worked an inverse function problem. We did those kind of like right before the winter break. And I'm thinking, I had some kind of thought about this. Oh, what we did back then was we kind of said, okay, find the domain and range of the original, and then we'll switch them for the inverse. I liked that. I really liked how we approached inverse functions this year. It worked really well for my sensibilities, and some people I know have very strong feelings about inverse functions for some reason, and it's like I really like the way we approached it here. So first, the domain of f is given to us 0 to 1. Wait. Maybe? Oh, no, because it's cosine of pi x. I see it now. Okay, great. All right. Domain is right here. I was really confused for a second. It's like, I don't like sine of 1, right? Or cosine of 1. But this would be cosine of 1 pi. So the domain is going to be 0 to 1. If I was to graph y equals cosine of 2 pi x, which, I think I'm going to. It's been a while since I've done that too. Remember, cosine starts off at the top, and then it goes down, and then recovers. So I'm just going to sketch one period. Okay, and because I didn't have a horizontal shift, there was no phase shift. It's been a while since I've done one of these. I'm starting there at 0. Period is 2 pi divided by b. 2 pi divided by pi, that's going to be 2. So I'm having 2 over there and 1 right there. Okay, that makes sense. This is an interval on which a domain, an interval inside the domain on which an inverse can be constructed because the function is monotone decreasing. Okay, if it's only decreasing or only increasing, then we will be able to take the inverse of it. Notice we're not interested in beyond x equals 1 because then the thing starts to wrap back on itself, and an inverse would start to spit back more than one value, which me personally I don't really have a problem with. But if we want the inverse to be a function, which we do for arcsine and arccosine and arctangent, we want like one agreed upon value, the most obvious place on the unit circle. That's what I'm saying here. Okay, and then, we've got midline is the number that we've added on the outside, which would be 0. Amplitude is looking like 2, so it'd be going from -2 to 2. All of this to say I've got a range -2, 2. All right, so if I want an inverse function, I'm just going to start by solving for x in terms of y, because that's the way I would prefer to approach it. So I've got y equals 2 cosine pi x. Okay, so I'm going to really try to solve for x. So divide both sides by 2. 1/2 y equals cosine of pi x. Okay, now I'm going to hit both sides with inverse cosine, arc cosine. So I'm going to have arc cosine of half of y equaling arc cosine of cosine pi x. Once we deal with the domain restrictions at the end, that's the nice part about this approach, where we just find the domain range first, we mentally switch them, and then we'll figure it out at the end. We don't have to worry about inverse cosine of cosine. It's just going to be pi x. And then I solve for x, and I'm going to say, all right, x is going to equal 1 over pi times arc cosine of 1/2 y. Okay. And that's going to be my formula for my inverse. If I need f inverse of x, did it request, and it just said an equation for the inverse, okay, that is an equation that represents the inverse in my mind. Okay, that if I needed, but maybe because this is the first one, I'll take you back through my normal process. I would say, all right, that means f inverse, x is f inverse of y, okay, because y is f of x. Okay, so I would just say this is really f inverse of y. You remember, you saw me do this a couple of months ago. And then what I do is I just go in and I replace each instance of y in the formula with an x. And I've got a formula for f inverse of x. Okay, that's what I would prefer to look at it as. Okay, now, the domain and range of this inverse function will be the range and domain of the original. So the domain is going to be -2 to 2. Okay, and that makes a lot of sense because then that makes the input values into inverse cosine being between -1 and 1. That's the type of thing we can do. And then over here, the range will be the domain of the original, and that will be 0 to 1. All right, now the next one here is 5 sine of 3x for x running from -π/6 to π/6. All right, so I'm going to give a quick sketch of this thing. Sine starts in the middle, and then goes up, but I like to kind of map it out this way. That looks like it's going to be good enough. Okay, there we go. So 5 sine of 3x, okay, no phase shift, so that's giving me the domain. I'm mostly interested in the range here. And if you just can see this sine is between -1 and 1, so 5 times the sine of the thing is going to be between -5 and 5. Great, good for you. Skip ahead 20 seconds. Period is going to be 2 pi over b. That's going to be 2 pi over 3. Who even cares about horizontal? I only need the range because I already have the domain. That's right here. Okay, midline is 0, amplitude is 5, so I go up to 5 and down to -5. That means the range of g is going to be -5 less than or equal to y less than or equal to +5. All right, great. Now I'm going to go about solving for the inverse algebraically. 5 sine of 3x. Okay, 1/5 of y equals sine of 3x. I'm going to take arc sine of both sides to get rid of the sign on the right side, right? You can't divide by sign, sign in a number, right? It's an operator. So I'm going to undo that by taking inverse sine of 1/5 y, and that will be equal to 3x. Okay, and then I'm going to solve for x, and I'm going to say x equals 1/3 of arc sine of 1/5 y. Okay, so now I've got a formula for the inverse. If I had called that f inverse of y, that would be 1/3 of inverse sine of 1/5 y. Okay, but I might be interested in, say, answering a multiple choice question and finding f inverse of x. So I could, plug in x into that formula, wherever I saw y, and then I'd have f inverse of x. And then on this one, okay, the domain and range, it's going to be very easy to do because we already did the work earlier. Right? We just swapped from the original. Domain is going to be -5 to 5, and then the range of the inverse is going to be -π/6 to π/6. Okay, including the endpoints. Intentionally closed interval because we can equal those values on the unit circle, right? Sine can equal 1 and it can equal -1. It can equal those extremes, whereas tangent cannot, where it'll have open intervals for its domain and range. Okay, I see it now. I was like, why do we need a domain restriction on this one? I was just talking about we don't need it. Okay, because it's going to end up being, it's kind of like a range restriction on arctangent, so we don't have a whole bunch of layers of that graph. Basically is what's going to happen. So I'm going to say, all right, this is telling me the domain. Okay, the range of tangent is going to be all real numbers. We'll come back on that later. Okay, I don't think I really need a graph now because the work I did on the other two on the graph was to find the range. Or really just to convince you of the range, because I think I was very confident what the range was, and I feel like a lot of my students are going to be confident on what the range is just by looking at the equation. But if you're not, I wanted to give you something a little bit better than here it is. Just look at it, or just remember this thing from 2 months ago or whatever. All right, so h of x equals 1/2 tangent of pi/4x. So I'm going to say, all right, solve for it algebraically. Okay, so multiply both sides by 2. Take arctangent of both sides. And then I suppose I will be multiplying by 4 and dividing by pi. It's a little strange, but it's all right. We can work with that. 4 over pi arctangent of 2y. Okay, so this is a function of y, so I would say h inverse of y is equal to 4 divided by pi times inverse tangent of 2y. And then I might, just say, all right, well, I'm just going to plug in x to this formula, and of h inverse of x is going to be 4 over pi arctangent of 2x. And then over here, the domain of this one would be the range of the original, and the range of this one would be the domain of the original, so negative 2 to 2. All right, and then j of x is going to equal 3 cosine of 2 times x minus pi over 4 plus 1. That is a lot going on here. Okay, I'm going to, because I'm back to the cosine world, okay, cosine is between negative 1 and 1. So this 3 cosine of a thing, that's going to be between negative 3 and 3. But I'm going to be adding 1, so I think it would be between negative 2 and 4. So it might be good for me to go and just give myself a little sketch. All right, cosine starts at the top. And it's never a bad time to practice, I mean, maybe not producing this, but thinking about the graphs of trig functions, because that's honestly it's far more important overall in AP Precalculus for the exam, and like the relative weights of the stuff is the graphs of trig functions much more important than arc trig, right? That's where we're just kind of like breezing through arc trig and reciprocal trig and moving on to more interesting things like polar. So this is kind of a picture of the graph. Who cares about the horizontal stuff, because I'm here to find the range. So the midline was 1, because I had a 1 on the outside, and the amplitude was 3, so I'm going to add 3 and subtract 3 from 1. And so I will see that, okay, I've got domain over here. Range is looking like negative 2 to 4. Okay, now I'm going to go about solving for this algebraically. Y equals 3 cosine of 2 times x minus pi divided by 4, and then add 1. So I just got to start solving at the x, and so I'm going to do reverse order of operations. Get rid of the addition and subtraction first. So I'm subtracting 1 from both sides. I still have 3 times cosine of all this stuff. And I'm committed to showing you all the steps, so I'm going to divide by 3. I can take arc cosine of both sides, and I just realized I've been writing, cosine -1 every time, and you don't feel like you have to do that. These are equal, valid, and you need to recognize that they're equivalent in AP Precal. You can be ready for either of those notations. And so if I take arc cosine of the cosine, that'll just leave me with 2 times x minus pi over 4. And I'm getting closer. I'm going to divide both sides by 2. 1/2 arc cosine of 1/3 of y minus 1. And that's going to equal x minus pi over 4. And I am pretty much there. I am going to add pi over 4 to both sides and say, all right, now I'll have x. That's going to be pi over 4 plus 1/2 arc cosine of 1/3 of y minus 1. Okay, that was a lot. So what I'm going to do is I'm going to replace x with f inverse of y, because that's what it is. And then I'm going to plug in x into that formula, like composition of functions. Just wherever I had seen y in the formula, I'm going to plug in x. All right, and so I've got a formula for f inverse of x. That one was pretty involved. I'm going to say, all right, domain is going to be -2 to 4. And then the range will be 0 to 3 pi over 4. Okay, and that's the end of this page. Yeah, I'm going to call it for this video and come back a little bit later and work the rest of this homework. And so I'm sure, like I've got it suggested somewhere on the screen here. Just like click there and it'll take you to the rest of the solutions for this homework. That's it for this one. Thanks for watching.